Okay, geometry video 2 for lesson 7.1 on dilation. All right, let's take a look at the next problem here. Okay, so we are now on a coordinate plane, and it says, what are the vertices of a dilation of a scale factor of 3? Now notice there's no center of dilation, so this means the center is the origin, as it says down here, and we're doing triangle ABC. So again, if I interpret what this means right there, right, it means we're going to do a dilation centered at the origin with a scale factor of 3. Well, when you do a dilation on a coordinate plane around the origin, you're going to get d of n on x, y. And what you're going to do, the rule, is that you're just going to take each set of coordinates, x and y, and multiply them by the scale factor. So, I don't know, I put a d there. I didn't mean to. Sorry about that. So when you do this dilation, your new point is going to be n times x, n times y. Okay? So all I'll do here is I'll identify the 3 ordered pairs. So A is at 2, negative 1. B is at negative 1, 2. And C is at 3, 0. And I'm going to simply take each set of coordinates and multiply them by our scale factor of 3. So I'll show the work for the first one. So A prime is going to be 2 times 3 and negative 1 times 3. So that means A prime is going to be at 6, negative 3. Okay, for B prime, I will multiply those by 3. So times 3 times 3, that's negative 3 comma 6. And for C prime, let me drag this away. Sorry about that. For C prime, I'm going to multiply by 3 and times 3. 3 times 3 is 9. 0 times 3 stays 0. And here are the new vertices. If I go ahead and graph that, and again, this is going to be a little bit off my picture, I apologize. So A is at 6, so 1, 2, 3, 4, 5, 6, negative 3. So there's A prime. B is at negative 3, 1, 2, 3, up 6, 1, 2, 3, 4, 5, 6. There's B prime. And C prime is way over there at 9, 0. So this is 4, 5, 6, 7, 8, 9, 0. And again, if I connect these with as straight a lines as possible, which is not going to be very good, this will be your, yeah, that was very bad. I got to fix that. Sorry, I can't let that go. This will be your new image. A prime, B prime, C prime. Notice that it is bigger because your scale factor is 3, so we did an enlargement. Right? But it is the same shape, just a different size, a little further away from the origin. Notice, because the origin is not in the triangle, you're getting farther away from the origin, so that's why we're up and to the right. All right? But there we go. So coordinate plane, pretty easy peasy, in my opinion. Okay, now a little bit more difficult. What are the vertices of a dilation 1/2 scale factor? What about the point R of QRST? So now we're letting R be our center of dilation. What this means is, right, R and R prime will be the same point. So this point will be R prime. And now this rectangle is going to shrink towards R. It's going to collapse towards R. Now, our scale factor is 1/2. Now, because my sides are horizontal and vertical, to find where the new vertices, Q prime, T prime, and S prime go, I'm just going to take the side lengths of the original rectangle and multiply them by 1/2. So, for instance, RQ, right? If I take 1/2 of RQ, that's going to give me the length of R prime, Q prime. So I know that RQ is 1, 2, 3, 4, 5, 6, 7, 8. So if I take half of 8, that's 4. That's going to be the length of R prime, Q prime. Well, if R prime is here, I just count 4 away. 1, 2, 3, 4. And there's where Q prime is. I'll do the same thing with RS. 1, 2, 3, 4, 5, 6. So I'll take half of 6 to get 3, and that is going to be R prime, S prime. So I know that S prime is 1, 2, 3 away from R. And then if I just keep the shape the same, I could look at the coordinates of of, no, I'm just going to keep the shape the same, right? So I have a rectangle, so there's r prime, q prime, there's r prime, s prime, and then I'll just go down and to the left, and this is the final coordinate of t. So to go in order, q prime is going to be at -2, 3. R prime is going to be at -2, 7. S prime is going to be at 1, 7. And T prime is going to be at 1, 3. And there are our new vertices. So be careful when the center of dilation is not the origin. It's not as simple as just multiplying the coordinates by the scale factor. Okay. Next, here we go. So scale factor and blueprints and all that fun. A great topic here. So it says a blueprint for a new library uses a scale factor of 1/50. Mr. Ayer measures the reading space on the blueprint to find the actual dimensions and the area so you can add furniture. What are the actual dimensions of the reading space? So this scale factor, right, n equals 1/50, right, is comparing I'm going to say a drawing to an actual length, right? 1 is the smaller, 50 is the bigger, right? So we're scaling it up, right? So if I look at this reading space, if I go along this bottom edge here, right, on the ruler, it goes to 14. So that bottom edge is 14 centimeters. And if I go along this edge here, 0, goes all the way to 12, so that is 12 centimeters. So these are the drawing lengths. So to find the actual dimensions, I'm going to use a proportion. I'm going to use 1/50 equals, now let's call, so 14 centimeters. Let's call that the length, right? So that is the drawing length. That's going to go on top. And on bottom, I'm going to put x, because what I'm looking for is I'm looking for the actual dimension. So this is the drawing dimensions on top. These are the actual dimensions on bottom. And it stays consistent between both fractions. So again, this is a proportion. We're going to cross multiply. So x equals, and when you multiply 14 and 50, you get 700. Now, notice that this scale, or the scale factor, did not have units. That's because it was the same units. So those same units are going to be the units on the scale, so centimeters. So this was 1 centimeter to 50 centimeters. So this x is in centimeters. Now, we do not measure reading spaces, rooms, in centimeters. We measure them in like feet. And in the metric system, right, feet, yards, those are all comparable to meters. Now, our conversion factor, I'm going to put it right up here. So 1 meter equals 100 centimeters. Remember, centa means 100, like century, right? So what I'm going to do now is I'm going to take this x and divide it by 100 to get the number of meters. And x is going to be 7 meters. And that is going to be that actual length, 7 meters. Okay, I'll do the same thing with the 12. So we'll create this proportion. So 1/50 equals 12 over x. I'm going to cross multiply to get, I'm going to do it right here, x equals 12 times 50 is 600, and then again we'll divide that by 100 because that's in centimeters. Let's call this y, not to confuse ourselves, so y, and y is 6 meters. Sorry for going this way with it. And that is your other dimension, right? So the actual dimensions of this room are 7 meters by 6 meters. And if you want to write it pretty, that'd be 7m by that x, 6m. Okay, so I think there's a second part here. Okay, part B. So what is the actual area of the reading space? How does the actual area relate to the area on the blueprint? So what I would do to find the area, it's a rectangle, is go length times width. So I'm going to do, to find the area, I will do, 7 by 6, 7 times 6, that's 42, and that's meters squared, okay? So that is the area of the actual reading space. Now, it says, how does the actual area relate to the area on the blueprint? Well, let's look at the area on the blueprint. The area on the blueprint would be, and again, this was 14 centimeters by 12 centimeters. So 14 times 12 gives us, handy in the calculator real fast, 14 times 12, 168. But that is in centimeters squared. I need to compare these using the same units. So I'm going to take the 42 meters squared, and I'm going to turn it into centimeters. Now again, if we do 1 meter is 100 centimeters, then 1 meter squared, if we square that, is going to be 100 centimeters squared. 100 squared is actually 10,000. Now, this case, because we're going from meter squared to centimeter squared, we're actually going to multiply by 10,000. And that's going to give us 420,000 centimeters squared. So what I'm doing right now is I'm converting the area, the actual area, into the same units as the drawing area, so I can compare them. And now if you look at this scale factor of 1 over 50, let's put the smaller number on top. So 168 over 420,000. Okay? And I'm going to go into Desmos real fast, so this is going to go away, and I'm going to divide that out. Okay, and we'll finish the problem in Desmos. Okay, so if I do 168 divided by 420,000, I get that if I press the fraction button. Okay, so if you compare the areas, you get 1 over 2,500. Now, the question is, how does that compare to the scale factor, which was 1 over 50? Well, look at this number 2,500, right? That looks awfully close to 50. Let's do something. Let's take the square root. I'll do it down here. Let's take the square root. Notice I typed that in, square root. You can use the button too, of 2,500. Ooh, you get 50. So that means, it went away, sorry. That means that 1 over 50, and if I square the 50, I'll get 1 over 2,500. Well, if you square the top as well, if you square 1, you also get 1, because 1 squared is 1. So here is the idea. If you compare the areas of two similar figures, their ratio is going to be equal to your scale factor squared. So we need to write that down. So we'll say the ratio. So write this down on your paper, of your notes. The ratio of the areas let me see if they use the word similar yet. Let me see real fast. I'll come right back. No. So they didn't. So we gotta come back here. Okay. So the ratio. The ratio of the areas is the scale factor squared. And this is something that's always true about similar figures. I don't recall if we talked about similarity in this lesson, but we will in the next one, so this is a good introduction. But similar figures, when you compare their areas, it's the scale factor squared, and that's because both dimensions are going to be changed by the scale factor. So when you multiply them to find area, you're going to multiply two of them. That is the scale factor squared. Okay? So this is sort of a state test question. So the ratio of, that should be the ratio of the areas is equal to the scale factor squared. Okay, thanks for watching, and we'll see you in class.